Welcome back from break. So now we are going to proceed to finish the topics for chapter 13. The first thing that we're going to mention is the whole idea of Fischer projections. Since earlier today, I mentioned to you guys that Fischer projections are a way to illustrate carbohydrates. We particularly use them in monosaccharides and other molecules that are chiral. So what is a Fischer projection? Fischer projections were actually invented by Emil Fischer in 1891. And this is a two-dimensional representation of a three-dimensional organic molecule, okay? So we use them in all areas of organic chemistry, but particularly for monosaccharides. This is what a Fischer projection is trying to show. All the bonds that we see that are horizontal are actually going to be showing us bonds that are actually facing us in terms of a plane. So technically, these are written as a wedge. Anything that is in a vertical line, these are the bonds that technically in these tetrahedral centers are going to be facing the back of the plane, okay? So this is kind of, let me actually get a molecular model so you guys see it. Give me a moment. Sorry, you guys. I actually took my molecular models back to my office since I'm starting in the fall and I forgot to keep it for at least a few more weeks. But anyways, you guys don't need to know how to draw a Fischer projection. The main thing that I want you guys to get out of a Fischer projection is that at every intercept between that horizontal line and that vertical line, there is a carbon atom. So understand, give me a moment. That there's carbon atoms at each one of these intercepts between the two lines. And similarly, fructose will have carbon atoms right here. So if you're given a Fischer projection and you're trying to classify a monosaccharide, depending on the number of carbons, please do not forget to know that at the intercepts, we have carbon atoms. The ones for this one are here. Now, another thing that we utilize in terms of stereochemistry is determining the D and L notation for monosaccharides. Remember, these molecules are actually chiral, okay? So if we look at, for example, the molecule of erythrose, okay? Let's put in the chat, how many chiral centers are in the molecule of erythrose? We have 4 carbons. How many chiral carbons do we have? 1, 2, 3, or 4? Let's put it in the chat. How many chiral carbons do we have in erythrose? It's not 3. Excellent. There's 2 chiral carbons. This carbon, the one in the aldehyde, is not chiral because it only has 3 things attached to it. Remember that by a carbon that is chiral needs to have 4 things attached to it. So that's why that one is not chiral. This one is a chiral center. This one is a chiral center. The CH2, of course. Yes, because of the double bond, that's why the first one is not a chiral center. So there's only 2 chiral centers, okay? So you can envision that in nature, we have enantiomers, because once you have a chiral center, you know, technically, even though we didn't go in depth into the definition, basically, if you have a chiral center, you're going to have an enantiomer. So how do we determine if the particular monosaccharide that we have is either D or L? Well, it is all about the location of the OH group on the chiral carbon that is the farthest away from the carbonyl. So again, looking at the molecule of erythros, this is the chiral carbon that is the farthest away from the carbonyl. See how the OH is pointing towards the left? That's why that's the L isomer. The D isomer is going to be the mirror image. So remember, these are enantiomers of each other. Look. The chiral centers are reflecting each other. So these are 2 enantiomers. Look at the molecule on the right. The OH is pointing towards the right, meaning for those of you that speak Spanish or know Spanish, they're towards the derecha. So if the OH is towards the right, derecha, that's why it is D isomer, okay? So if you're giving a monosaccharide, again, by finding the chiral center that is the farthest away from the carbonyl and knowing if the OH is towards the left or towards the right, you can determine if it's D or L notation. This image that you guys see here, it was sent to me by, my friends that are also organic chemists, that they found it on internet many years ago. And this is just, a little meme of this D and L notation. As you can see, the image on the left, Samuel L. Jackson is looking left. So then it's an enantiomer, which will be Samuel D. Jackson is looking towards the right. So if that picture helps you determine D or L notation, hey, use it. But in general, we already talked about how in chemistry we define if a particular monosaccharide is D notation or L notation, okay? In the chapter quiz for chapter 13, you will see that there is an exercise of looking at the different molecules, which ones is D or which one is L. Now let's focus on the monosaccharides, okay, that we commonly see around. And those are going to be glucose, fructose, and galactose. What is glucose? Glucose is a monosaccharide that is found in fruit, in corn syrup, and even in honey. It is an aldohexose. That means that it has an aldehyde, as you can see the structure on the right, and it has 6 carbons. So that's why it's an aldohexose, and it has the chemical formula of C6H12O6. Now, sometimes glucose is not referred as glucose. It is also known as dextrose, okay? And whenever they're measuring the sugar in your blood, what they're looking at the glucose levels. I have seen reports in the media of like, oh, dextrose is a really bad chemical. It's, it's poisonous. And I'm like, they're just saying that sugar is poisonous. And too much sugar, as we know, from what we hear in the medical community, and of course the doctors are always keeping track, the problem is that if you have too much sugar in your blood, then you can develop conditions like diabetes, and there's complications that are tied in with diabetes that they can lead to death, okay? So understand that whenever it comes to diabetes, You don't die of diabetes, you die of the complications that come with it. Heart disease, poor circulation, blindness, blood pressure problems, obesity. So I know that at times people are like, oh, diabetes is just, you die of diabetes. No, you die of the complications that come with it. So that's why it's important to, regulate the sugar. Too much sugar, like anything in life, too much sugar, too much fat, it's not good for your health. So it always needs to be regulated and observed. Now, why is glucose so important? Because it is the building block for disaccharides like sucrose, lactose, and maltose, but it's also the building block like for polysaccharides like cellulose and glycogen. So understand that glucose is going to be the preferred sugar. And when we are deriving energy from a monosaccharide, remember that glucose is the one that we are producing that energy from. We also have galactose. And galactose, as you can see, is the second molecule that we have here. Galactose is also an aldohexose. And as you can see, it also shares the chemical formula C6H12O6. Now, galactose, we don't find it as a monosaccharide in nature. Okay, we obtain it from lactose, okay, which is a disaccharide that has galactose. Now, when we look at the structures between glucose and galactose, there's only one difference, and that is on carbon 4. On carbon 4, we can see that the OH, okay, for galactose is pointing towards the left, and in glucose is pointing towards the right. So as you can see, that simple difference gives us a brand new sugar with brand new properties. So because this happens at a particular point in the carbohydrate, the relationship between glucose and galactose is that galactose is an epimer of glucose. And that simply means that they are going to be different from each other structurally at one carbon atom. And it has nothing to do with D or L configuration. Okay? There are other epimers of glucose that include mannose, okay? So understand that I'm just giving you an example of one of the epimers from glucose, which is galactose. Let's now deal with fructose, okay? Fructose, we actually obtain it from sucrose, which is table sugar. Remember, sucrose is a disaccharide. So fructose has also the chemical formula C6H12O6. And out of the monosaccharides, it is the sweetest out of the monosaccharides. It is so sweet that it is actually twice as sweet as table sugar. Where do we find fructose? Is one of the main monosaccharides that we find in fruit. Okay, so when fruit is nice and ripened, what your mouth is detecting, other than some of the glucose that is in there, is some of the fructose that is in the molecule. Now, when we compare fructose to glucose, fructose is a constitutional isomer of glucose, simply from the fact that when it comes to the attachment of the atoms, we have a ketone in the fructose and an aldehyde in the glucose. So that is the relationship between the two. Any questions when it comes to monosaccharides? One of the things that monosaccharides can do is that monosaccharides can actually undergo cyclization. This reaction we didn't actually discuss in chapter 12, but understand that this reaction is important in nature because monosaccharides can actually do what is called an intramolecular reaction. Intramolecular, not inter, so intramolecular reaction. Because all the atoms that are involved in this reactivity are within the same molecule. So when a monosaccharide undergoes this intramolecular reaction, it can actually form 5-member rings or 6-member rings. And those adapted structures are actually very favorable, okay? Now, whenever we have monosaccharides being illustrated in these cyclic structures, we know these as Haworth projections. So these Haworth structures is what you guys see here, okay? So how is this accomplished? Let's look at the case for glucose. So here we have the structure of glucose. Again, the reason why this is labeled D-glucose is because the OH is pointing towards the right. Carbon number 5 is the chiral carbon in this system that is the farthest away from the carbonyl, okay? You can see from the structure that glucose has 4 chiral centers, carbon 2, 3, 4, and 5. They're all chiral. Make sure that you review that. There is a problem in the chapter quiz that you are given carbohydrates and you need to determine how many chiral centers are in it. So make sure that you practice based on what we did in class today. So as I said, in this molecule, it is known that the OH group on carbon 5 can actually react with the aldehyde motif that is present in this glucose molecule. So you can actually redraw that glucose molecules to put them in close proximity. Overall, understand that what happens in this reaction which this reaction name is called hemiacetal formation, from the idea that, let me just rewrite it right here so you guys can look at the hemiacetal. This functional group is called a hemiacetal. Understand that a hemiacetal is not an ether. Because in this structure is actually resulting from an alcohol reacting with an aldehyde, okay? So that is not an ether. So when it comes to this process, we see that the OH that was attached on carbon 5 forms a bond with the carbonyl, okay? So if we keep track of the atoms, this oxygen is this oxygen. In the process, we create a brand new bond. This oxygen is this oxygen. And in the process, there was a proton transfer from this hydrogen to this one, okay? Why is this reaction important? Because as I just mentioned to you guys, glucose, when it is in open form, has 4 chiral centers. This, and this. Once this cyclization has happened, we have one more created. So when glucose and other monosaccharides are now cyclic, these molecules have 5 chiral centers. So this one is the new one form. If you want to keep track of the numbers, let me just write them here because they were not put. 1, 2, 3, 4. Oh, wait. Let me just use the correct numbering. This is carbon 1. This is carbon 2, 3, 4, 5, and 6. So the previous 4 chiral centers are still here. 2, 3, 4, 5. So we just created this new one. In this new position where the hemiacetal is formed, actually has a particular name. It's called the anomeric position. So again, the anomeric position results from the reaction of the OH group on carbon 5 and the carbon in the carbonyl on carbon 1. Now, because the attack of the oxygen can happen towards the back of that carbon or towards the front of that carbon, the anomeric position can adopt 2 different conformations. The OH in the anomeric position, if it's pointing up, is known as beta. That's why you guys see that beta right there in the corner. So if at the anomeric position, which is always in that corner in a cyclic monosaccharide, is always there towards the right, is the first carbon on the right when you look at the bond from the oxygen. That's where the anomeric position is. If the OH at that position is pointing up, that is the beta conformation for your monosaccharide. If the OH is pointing down at the anomeric position, that is known as the alpha configuration, okay? So how you're gonna remember all this alpha beta stuff? Because you can just look at the word, and this is how I did it in graduate school. I actually came up with this in graduate school at Buddha. So if you know the word Buddha, looking at a cyclic sugar or monosaccharide is not that difficult. You need to know where the anomeric position is. And as I just mentioned to you guys, it is the first carbon where you're coming down from that bond, okay? You look at the OH, it's going to be beta if your OH is up. Is going, if it's down at the anomeric position, the OH, then that means that that is an alpha monosaccharide. So as long as you remember Buddha, you know where the anomeric position is, determining alpha or beta shouldn't be too much of a hassle. Any questions about Hayworth structures? You guys don't need to know how to draw them, but you need to know how they are produced. And you can see the words in the second bullet point, how that hemiacetal, which is the functional group that we see there, is formed from the carbonyl group and the hydroxyl group in the same molecule, coming together to form it and giving rise to the anomeric position. Any questions about Hayworth projections? Then since there are no questions, let's continue talking about the chemical properties for monosaccharides. Starting with looking at the formations of sugar alcohols. So sugar alcohols, as you can see, okay, in case you're wondering, sugar alcohol is not when you put sugar in your alcohol, okay? Sugar alcohol is actually a compound. How are sugar alcohols produced? As you can see in the first bullet point, sugar alcohols are actually synthesized by doing the reduction of a particular monosaccharide. You can also do it on disaccharides, okay? All you need to do is that when you look specifically at the molecule, okay, if they undergo reduction, we learned this reaction in the previous chapter. When we look at the functional group and what is happening, the aldehyde turns into a primary alcohol. Look at the reagents. It is the hydrogenation conditions that we learned before. Now, where do we see sugar alcohols? They're actually utilized as sweeteners in many sugar-free products, okay? Diet drinks also have them. Sugarless gum for sure has them. That's where we see them. You can actually buy them in bags. Like when you see the erythritol, xylitol, okay? There's all these products. There's actually candy made out of sugar alcohols, okay? Now, how do you know what is the sugar alcohol that is going to be formed, or what is the carbohydrate that they come from? Well, the name for your sugar alcohol is actually determined by removing the OSE ending in your monosaccharide and replacing it with ITOL. So for example, here we have glucose, okay? If you remove the OSE and you place it ITOL, that gives us the name of glucitol. Glucitol, which is also known as sorbitol, again, it is something that our receptors detect as sweet, but we don't utilize it to derive energy. That's why it's sometimes you see it as 0-calorie sweeteners, okay? Among the wide array of no-calorie sweeteners that are out there. This is just the sugar alcohols. So that's how we know that glucitol is made from glucose, because you could do the opposite. If you remove the ITOL and place the OSE, that's how you know that glucitol actually came from glucose as a molecule. If we look at this sugar-free gum, okay, you can see sorbitol here, which is another word for glucitol, but we also see another sugar alcohol. Let me point it out. Here we have mannitol. So my sugar alcohol is mannitol. Okay, so to determine where mannitol, which actually made from, all I have to do is remove the ITOL and replace it with OSE. So mannitol actually came from the monosaccharide mannose. One that is common, that is out there, people use it a lot, is xylitol. What carbohydrate does xylitol come from? What is the name? Just put it in the chat. What is the carbohydrate that we utilize to make xylitol? Excellent. Xylose. One that I haven't seen often, but I know it is commercially available, is the sugar alcohol that comes from lactose. What would be the name of the sugar alcohol that is made from lactose? Again, we're replacing the OSE, including ITOL. Excellent. Lactitol. In the in-class worksheet, you guys have a table in order to determine what are going to be the carbohydrates in sugar alcohols. But understand that these sugar alcohols are made by the process of reduction, of taking the aldehyde in the functional group and turn it into the corresponding alcohol, primary or secondary. Another type of carbohydrate that it is out there and it is consumed by people is artificial sweeteners. Okay. Put a 1 in the chat if you have heard of artificial sweeteners. Okay. Some people avoid them. Some people love to consume them. Okay. My take on it is that everything has to be done with proper dosing. Okay. Everything needs to be used in moderation, because I have heard in the line of different coffee places, especially if I ever have gone to Starbucks, people asking for amounts of artificial sweeteners that I'm like, wow, that is interesting. Give me 8 pumps of Splenda. I'm like, wow, like Splenda is super sweet. And you want 8 pumps of that? Interesting. But again, let's just study. We're going to learn about artificial sweeteners. So let's learn about it. So it is true. Artificial sweeteners gives you the sweetness without the calories. That is very true. Okay. They are chemical compounds that are designed to replace sugar in your diet because they stimulate the receptors in your tongue to detect the sweet flavors. Now, this is the thing. Let's look at them structurally, okay? Because this is chemistry. These are among the 3 that we mostly see in the United States, starting with the one on the left, which is Splenda, okay? Splenda, which sometimes you don't even see Splenda. Now, food products actually use the word sucralose, and people are like, oh, it has sucralose, it has table sugar. I'm like, sucralose is not table sugar. Sucralose is an artificial sweetener. Sucrose is table sugar. So don't be confused by that. Sucralose is, that's why like the commercial for Splenda says made from sugar, but it's not sugar. That is true. It's made from sugar because the difference between sucralose or Splenda and table sugar is 3 atoms. 1, 2, 3 chlorines. That's it. You replace those OHs with chlorines and boom, you have sucralose. Now, let me tell you guys something about artificial sweeteners. We are using them commercially because they're used in many food products. We do not understand what they do in the body, how the body processes them. We have no data on human subjects on the use or overuse of artificial sweeteners. So I just want to put that out there. I hope that at some point people get interested on this, because even though at first these molecules were, designed to give people that maybe cannot consume sugar because of different conditions. give them the ability to try molecules that are sweet and, you know, add them in their food products. The overuse of artificial sweeteners is so intense, and we really do not understand, you know, the effects on the body, which is the scary part for me as a chemist and biochemist. So we don't understand what happens. The only thing that I have observed in my years of looking at the research for all of this is just animal data. And some of you out there will be skeptical and be like, well, what do I have in common with a mouse? What do I have in common with other animals in the laboratory? 97% of the genes and proteins that process all of this. So that's why in the laboratory, you guys, we go through a whole process of using cells and then animals and then bigger animals. All of this in order, again, for some products, not these, have to go all the way to monkey before they even come out. Artificial sweeteners, I don't know how they pass the test. And again, we don't understand the effects on human. At least, even doses, we don't. Technically, this we're supposed to use in small amounts. And you guys can go to the grocery store and see that you can buy bags of Splenda for baking, for cooking. For me, it is scary. But again, that's my personal opinion. So in animals, they have seen that at higher doses of artificial sweeteners, there have caused seizures, liver failure, kidney failure. So basically the filtration systems in your body are being affected when, again, these products are consumed in high amounts. But again, they're animal models. So what they were trying to replicate is people that consume this in really high amounts. And trust me, you know, some of you may think like, what? There's people that consume it in this high amount? Yes, every day, all day. Because another thing that has been discovered in animal is that this causes addiction. Like your brain, I don't know if you guys have friends, and if this is you, please don't feel offended. I personally, I'm talking about my experience. I'm not trying to attack anybody. That say, oh, I'm craving a Diet Coke. I've had friends personally say like, oh, I'm craving a Diet Coke. What are you craving? The artificial sweeteners. Because that's what is in there. So again, all the data that we have out there is just from animal models. So let me give you Splenda. Second one, aspartame is the one that is in Diet Coke. Now, we have seen monosaccharides. Does that even look like a sugar? Look at aspartame. That's in NutraSweet. What do you guys think? Aspartame, does it even look like a sugar? We've seen sugars. Does it look like a sugar? Right? It doesn't even look like a sugar because it's not. Aspartame actually comes from linking two amino acids together, aspartic acid and phenylalanine. We are going to learn about amino acids. Okay. And voila, that is aspartame. So whenever you see that certain products say it contains phenylalanine, if you look at the sugars in there, most likely it has aspartame. So again, Diet Coke has Diet Pepsi, most of those things that have diet have aspartame in it. At some point, baby formula had aspartame, but they have to remove it just because it could be toxic for certain babies that have not the genetic makeup to deal with the phenylalanine. So I think baby formula nowadays, you can get it without aspartame. The last one that we have here is saccharin. Saccharin is actually sweet and low. That's what saccharin is. Some countries have even banned saccharin. We still use it in this country. Okay. Now, the point that I'm trying to make with all of these artificial sweeteners is that understand that there's products out there for detecting sweetness, but I'm going to show you guys now, when we have these products, how does it compare to table sugar or to other monosaccharides, okay, in terms of the sweetness levels. When it comes to stevia, stevia comes from plants. Stevia is just, I think it has 3 carbohydrates in it. I haven't looked closely at stevia or seen reports on studies on stevia, even in animal products. It was just a solution just because it was, obtained from plants. When it comes to stevia, you just have to watch, because some stevia, I read my labels, you guys. I have mentioned this in class. I encourage you guys, because now you have chemical knowledge, read your labels. Depending on the product for stevia, you may have to check, because stevia sometimes is mixed with artificial sweeteners, just because that's how people are commercializing it. So be careful if you're trying to get stevia, that you read the label and it says stevia in it. Because sometimes if you don't read the label carefully, it's stevia plus other artificial sweeteners. Anyways, so let's talk about how sweet is sweet. So in table 13.2, we have a table which we are assigning, and this is all done in the laboratory, through different detectors. We are assigning a value of sweetness to the different types of sugars that we have talked about, okay? So understand that when it comes to the monosaccharides, and I mentioned this before, fructose is sweeter than sucrose, which is our baseline. So sucrose is 100, because that's table sugar. Understand that out of other disaccharides and monosaccharides, fructose is sweeter than table sugar. When it comes to the sugar alcohols, you can see that only xylitol is as sweet as table sugar. Look at the numbers for artificial sweeteners. How sweet they are compared to table sugar. Aspartame, 18,000 compared to the 100 of sucrose. Saccharin, 45,000 units compared to the 100 of table sugar. Sucralose, 60,000 compared to the 100 on sucrose. All I'm trying to illustrate here, you guys, is just that, and I don't know if this has been an experience that you have had, or maybe you have heard people say this, of if they drink a lot of Diet Coke and diet products, and then they have something with regular sugar, they're like, oh, this has no sweetness at all. That's when you realize, wait, is it that now my receptors are used to just higher levels, and then having a biomolecule, or here, monosaccharides or disaccharides, that have a lower sweetness level, then my detectors are like, no, that's not sweet enough. So this is just to illustrate, you guys, that when it comes to artificial sweeteners, make your decisions, because I'm not here to tell you yay or nay, but be conscious. You guys have a chemical knowledge about this. If you're going to use them in moderation, but always, understand that there's data, not in humans, but data out there that explains the use of these artificial sweeteners, okay? So we get to make better decisions, when it comes to artificial sweeteners. So continuing on, talking about the chemical properties of monosaccharides, let's talk about reactions that actually break down these carbohydrates, okay? So I mentioned to you guys in the beginning of today's lecture that we have monosaccharides, disaccharides, and polysaccharides. Hydrolysis is the process of cutting molecules with water. This process is actually done in the body whenever we're utilizing carbohydrates in order to resources as energy. Now, understand that out of monosaccharides, disaccharides, and polysaccharides, only disaccharides and polysaccharides can produce monosaccharides by hydrolysis. A monosaccharide cannot be hydrolyzed. As you can see, no hydrolysis, because you already have a single unit of sugar. So from one unit, you cannot break it down to half a unit. So monosaccharides are the only type of carbohydrate that doesn't undergo hydrolysis. If you have a disaccharide, of course, you're going to make 2 units of monosaccharides. If you have a polysaccharide, you make many, many units of monosaccharides. The last reaction that you guys need to be aware of is oxidation. But this reaction we actually talked about, and in this week's lab, you guys are also exploring chemical reactions done with carbohydrates. So in the last chapter, we talked about chemical tests. And as we mentioned, oxidation of different aldehyde groups, okay, via toluenes, and here is Benedict's, can be accomplished. Now, why is it that we focus on Benedict's reagent when it comes to monosaccharides? Well, because remember that the Benedict's reaction requires a molecule in which you have that aldehyde group, and adjacent to it, you will have an OH. So as long as your molecule has that, like many monosaccharides do, then the Benedict's reagent will be able to oxidize the sugar, okay, from aldehyde to carboxylic acid. In the process, your copper reagent is being reduced by the sugar, okay? So whenever you have a monosaccharide or carbohydrate for that matter, that is able to be a positive result, meaning that we're changing from blue to, green or orange or red, or in terms of the colors of the reagent, understand that we consider a reducing sugar. So a positive test in the Benedict's reaction means that you have a reducing sugar. Again, the term reducing is because the sugar undergoes oxidation, but your Benedict's reagent undergoes reduction. So that's why we call it a reducing sugar. Let me just write here the definition. Reducing sugar means that we're going to be reducing the copper, which is copper 2, in the Benedict's reagent to copper 1, and a change of color occurs. As you can see, if your Benedict's change into green, that means that you have traces of that reducing sugar. If it changes to orange, that is a moderate amount of a reducing sugar. If you have a large amount of reducing sugar, then it's going to change into that brick red solution. Because if you leave it in blue, then understand that blue means that either there's no reducing sugar or you have a control reaction because you have water. Any questions on the chemical properties for carbohydrates? Then let's move on to talk about the last two groups of carbohydrates that we have in this chapter, starting with disaccharides, okay? So when it comes to disaccharides, we have a number of digestible disaccharides that we can find in food. You can see that we have sucrose, which is table sugar. We have lactose, which is milk sugar. And then we have maltose, which is malt sugar, okay? So how is sucrose at the chemical level? Sucrose is a combination of glucose and fructose, okay? So Sucrose actually is linking these two molecules, the glucose and the fructose, at their anomeric position, okay? So the link between that glucose and fructose, it is actually known as an alpha beta 1,2 glycosidic bond. So whenever we have two sugars linking, that's what we call glycosidic bond, okay? So when you have two monosaccharides committed into a bond via their anomeric position, that means that they cannot go from ring form, as we see here, into an open chain. And in sucrose, that happens specifically. So that glucose and fructose, now that they're holding hands via their anomeric positions, they cannot open the chain. So that means that if you do the Benedict's reaction on it, you will never find aldehydes in it. So that means that sucrose is actually a non-reducing sugar. So if you do a Benedict's reaction with a sample of sucrose, you guys, it will remain blue. Lactose is a disaccharide that is found in milk and milk products. What is it composed of? Galactose and glucose. Now, the linkage between the galactose and the glucose is known as a beta 1,4 glycosidic bond. Now, because here in lactose, technically, this position, which is the anomeric position for the glucose, is still available, then this sugar can actually open and reform the aldehyde. And in the Benedict's reaction, if you put a sample of lactose, it will actually change color. Because lactose is able to open its chain, be oxidized, and that's why it's labeled as a reducing sugar, okay? Let's look at the last example, maltose, okay? I don't know who I'm speaking to out there, but I know I grew up on this. Has anybody out there, put a one in the chat, heard of or tried this drink that is used in Latin community that is called Malta? Has anybody tried Malta? Anybody put a one in the chat? It's this malt drink that they gave us, at least they gave me as kids. Anybody has seen Malta? No, people haven't tried Malta. I guess that's the thing. People don't know Malta? Let me see if I can find a picture of Malta and put it in the chat. No, people haven't heard of, it may be a Caribbean thing. Let me see, Malta, India. It's just, just imagine like, it looks like, let me see if I can put the picture. Copy image, paste. Did it paste? No, I didn't like it. Let me see if I can find a picture of Malta. And nobody has heard of Malta? Oh my God. Malta is this malt beverage. Look it up. Oh my God. It's, I don't know why we have that, but that is just a treat. They'd be like, oh, if you behave, you get Malta. Wow. Anyways, Malta, full of maltose, because it's made out of malt sugar. So it has the look of like Guinness in terms of beer. It's like that, but it's sweet. It's super sweet. Anyways, going back to maltose. Maltose is a disaccharide that it has two glucose molecules, okay? Now, these two glucose molecules are linked to one another by an alpha 1,4 glycosidic bond. So what that means is that here, we still have one anomeric position that is able to open. So when you put maltose in the context of a Benedict's reaction, it is also considered a, yeah, see, it looks, I don't know, you guys, don't try it because I said it. It's just one of those things. Yeah, Malta Goya, it could be any. In Puerto Rico, we have our own brewery, it's India. So we have Malta India. Oh my God. But it's just, yeah, it looks like Coke, but I'm just saying, you guys, Malta is an experience. And being a kid growing up in Puerto Rico, that would be like what you get like during recess, you go and get a malta and your little cookie. I'm like, wow, we were sugar high growing up. I don't know, you guys, if you try it. I haven't had malta in such a long time. And now I look at it and I was like, oh my God, I've never given it to my son. Anyways, but when it comes to maltose, understand that if we put it in the Benedict reagent, because we have that that anomeric position in one of the sugars, we are able to see that this is a reducing sugar, okay? Lastly, we are going to talk about polysaccharides. And I don't buy it. I think he's never seen it. I think maybe my mom has tried to give him malta, but then he doesn't even like soda. My son is a water drinker. Rarely. This kid he's very special. He's like, he doesn't like juice, nothing. He likes water. He drinks everything with water, all his meals with water. Yeah, he's good. I'm like, wow. Like for me, I like water, but then I like, my new thing is like the powder electrolytes. That's what I drink with my water. Like Sip Fizz or Ultima, those are the ones that I go for. Going back to the polysaccharides. So the polysaccharides that we are going to talk about are all polymers of glucose, okay? And polysaccharides in general are a form of monosaccharides, but understand that the ones that we are going to talk about in class are made out of glucose. We are going to mention what is the difference between amylose, amylopectin, cellulose, and glycogen, okay? Which are the four that you see here. Starting with amylose and amylopectin. So whenever you have a food product that has starch in it, like bananas, like potatoes, okay? In starch, we actually have two polymers. One is called amylose and one is called amylopectin. What is the difference between them? Well, pretty much that one is a straight chain of glucose that are linked together by alpha-1,4 glycosidic bonds, and that is what we find in amylose. Then we have another one that has that connection, but it has branches that are given by an alpha-1,6 glycosidic bond, and that is amylopectin, okay? So understand that in starches, we have two polymers, amylose and amylopectin, and the difference is that amylose doesn't have branches, amylopectin does. But when we consume them in our body, these are going to be hydrolyzed, and that's how one of the ways that we obtain glucose from food. Now, what do we do with extra sugar? We can store it. We actually have storage of sugar, and we store it in the form of glycogen. We store glycogen in liver and in muscle, okay? So when it comes to this, glycogen is, again, how we store sugar. And for example, there is a common practice for those of you that engage in running activities that sometimes, depending on the race, sometimes they have like pasta night the night before your big marathon or half marathon. I did not participate. I did a half marathon in June, but I didn't do the pasta night. But some people eat a lot of starch because they were trying to increase their glycogen storage, okay? Because they know that throughout the race, you need energy. So having, glycogen storage that a little bit on the high side, then you are going to be able to conquer those 13.1 or 26.2 miles. But in general, again, we store sugar in the form of glycogen. When we look at the structure for glycogen, it looks like amylopectin. It's just that it's more highly branched. But again, it is made from those glucose units. And you can see that in our cells, we hydrolyze that glycogen to maintain blood glucose levels, in between meals, or if you're doing exercise like a half marathon or a full marathon, just to maintain your energy throughout. The last polysaccharide that we're going to talk about is cellulose. And cellulose is what gives the rigid structure to the cell walls in wood and in fiber. So whenever you're consuming fiber, what you're consuming is cellulose. Now, when it comes to this polysaccharide, it is important to note that in cellulose, we have beta-1,4 glycosidic bonds connecting the glucose molecules. Us humans cannot take fiber, break it down, and use it for energy, okay? So when we take fiber, it is taken in, and then sometimes we have soluble fiber, right? Like right here, it says like in general, cellulose specifically cannot be, it's not soluble in water because it cannot hydrogen bond with water. It actually hydrogen bond with itself rather than with water. But when we are consuming this type of fiber specifically, what is helping our body is with the digestive system, but it's more because it's helping all the stuff that you want to push out of the body, like secrete it out when you're going to the bathroom number 2. Okay, that's what the fiber is helping for you to have bowel movements. It's not utilized for energy. So I know that out there, there's people that say, and maybe you guys have heard of this before. Oh, eat celery because that has negative calories. Celery, your body spends so much energy breaking it down to use it for energy that then that's why it's called a negative calorie food. There is no scientific evidence on that. Celery has good properties. It has water. It has phytonutrients that are in any leafy green or green vegetable. That I give to celery, yes. But your body is really not spending any energy breaking down that fiber in celery because we cannot process it, okay? The cellulose that makes those fibers in celery are resistant to hydrolysis because we don't have the biomolecules to utilize it. So understand that this whole idea of like negative calories in fibrous fruit or fruit or vegetables, it is something that has no scientific evidence because, again, when you take microbiology, you understand about the microbes out there. In our stomach, we don't have ones that can process cellulose. Other animals can, like cows. Cows like have, several stomachs and they can process some of this, but we cannot use it for energy. So for us, it's literally we consume it and it helps our bowel movements, okay? But understand that cellulose out of these is the only one that has beta-1,4 glycosidic bonds, and we cannot break it down. So this is the end of the chapter.